Okay, hey, hi everyone. Good evening. Very happy to be here. More so because it's in Kormangla. I was just telling Shubhi that this is almost like my second mom's place. I just love coming to Kormangla, and definitely happy to see such a vibrant crowd here. Uh, I think a few years ago, I used to ask, have you used Swiggy? I think now I would ask the other way around. Is there someone who doesn't use Swiggy? And in fact, if there is, this talk is about them, like who would be the new users of Swiggy and Instamart, and what is the kind of recommendation that we are going to give. Just to take a step back, if we just think of our life right from the time when we get up, I think in fact there is an app to make us get up, and then like it would have calculated your sleep and calorie, your fitness and everything. And there's obviously something like Instamart to order your groceries, food. Then there is some app to book your cab, make your holidays, restaurants, dine outs, book a date, whatnot. I think every aspect of our life is now kind of driven through an app. And once you get onto that app in this digital era, there is like loads of information. Unless there is some way of giving you a relevant information, there is no way. Like user is so overwhelmed by the amount of information that is there. So that's when we have the recommendation engines coming into picture, which can give you some relevant information among the sea of information that is present. A very typical recommendation system would look like this, where first among the huge corpus of information, we would kind of condense it to a smaller bucket, where that is the candidate generation. And among the candidate generation, you would want to rank it based on the relevance to the user. And then maybe when it comes to practical recommendation systems, there'll be obviously some business logic that needs to be applied, and that goes into the re-ranking layer. So this is like typically the recommendation system that you would see like all across the applications. And in some form of the other, maybe there are some small changes. But then all these recommendation systems work well if we have some data about the user. Say, for example, if I'm a biryani lover and Swiggy knows I'm a biryani lover, I open the app, it is going to recommend all the Meghanas and Paradises and let me know, okay, the biryani, right? But as soon as I enter the app, if it doesn't know, like, what are my choices? Am I a biryani lover? Am I an ice cream lover? If there is no data about the user, then what do you recommend? And that is what is a cold start problem, which all these recommendation systems suffer from. Now, in this talk, I'm going to cover the cold start problem more so from an Instamart angle. And this is a work which we did along with my colleague Bhavi. In Instamart, I'm sure you would have used, if you're a repeat user, like you've used the app multiple times, you've ordered from, this is the app you would see, your go-to items. It basically consists of those products which you would have ordered in your recent past, and that would be sorted through a ranking algorithm based on the periodicity of the item. Say milk, it's ordered every day. Say maybe a 5 kg atta, it might be once in a month. And also based on other preferences, that could be your brand affinity, and based on all those things, there is a ranking engine running, and these items would be ranked. But when we come to the new user, or say, for example, like early repeat users, as in like you would have made just say 1 or 2 orders, then what do we recommend? The most baseline that is used mostly everywhere would be like the popularity based, as in what is mostly popular in that area. That is what we would recommend. Say, for example, what is popular in Bangalore might be in the early morning slot would be something like maybe Nandini milk and maybe some eggs and some Britannia bread maybe. And in the afternoon slot, some veggies maybe, and so on and so forth. So based on the location, based on which pod the customer gets assigned to, like whether it is in Bangalore or Delhi or whatsoever, whatever is popular in that area, that is the best we can recommend. Which means to say that even if I'm, say, a ice cream lover, and say, for example, one of my favorite ice cream restaurant is out of service now, let's say it's at 12:30, then I would probably switch to Instamart and try ordering an ice cream. Maybe the first time I'm coming there. But why would you show me something like, say, atta or something else, or maybe something which is more relevant? Maybe it could be chips and thumbs up. I would never order. I mean, not for that, not like anything against chips or thumbs up, But yeah, generally I'm not a orderer of soda. Then why would even like, but I'm sure in our platform, that would be probably the highest selling item. But the popularity model doesn't work for me. I'm an ice cream lover. Like, can you show something else? Then that's exactly what we want to ask. But as you all know, no magic in ML can happen without data, right? Now, for the new user, where do I get data from? That's the question people were asking. Is there any way? I'm sure there are other domains or other areas which the customer is interacting with, right? I mean, this is not the only app people are interacting with. If I'm a Swiggy user, I might also be like maybe a Myntra user, or I'm also a Make My Trip user. So there is other business or business verticals within the same business where the customer is interacting with. So is there any way we can get that data, make use of learn the customer preferences from that domain and make use of it in the new user recommendations? And that's exactly what's the motivation behind using cross-domain data to improve the recommendation for the new users. And that's where we have this whole field of cross-domain recommendations coming into picture, where we have a source domain where there is rich data. Say, for example, if I take the Swiggy app itself, there is a Swiggy food app being the more like a slightly older app. There's a lot more users than maybe more recent, the Instamart app. So in which case, is there a way where we can use the customer preferences from the food app onto the Instamart app is what we are trying to do. Yes, we can, provided there is some overlap between the users who are operating, and also there is an overlap in the preferences itself. Say, for example, if a data shows me that there is no way a ice cream lover on food app is ever going to order, or is going to order equally among all the categories of Instamart, then there is no, if I show ice cream or not, it is not going to make any difference. So one thing, is there an overlap? Yes, we found out from our data, yes, there is a good overlap. And is there any correlation that between the categories of the preferences? And that's exactly, we started off with our EDA. Just to get to give you like how we did the EDA, there are different categories the food is divided into. Say, for example, this is some pesto tofu panini. I'm sure I've never had it, but it looks like anything in between, I think, Subway and some toast and sandwich. Okay, sorry, panini lovers. Yeah. So if I had seen this before, I wouldn't even know which dish category it belongs to. I think the same thing is true for Chicken Dominator. I mean, is it a burger, pizza? Is it a coffee? I don't know. Or maybe, I don't know. Okay. So now there is a food taxonomy, which is a Swiggy in-house built taxonomy, which is able to categorize each and every item to these food categories. That is, it tags each and every item on our menu as to what is the dish family it is, what is the dish subcategory, category, and the cuisine. So this is like otherwise, how will you even recognize what this string means, right? I mean, at the end of the day, if you don't even know the item, it's just an English string. So there is an in-house taxonomy, that is a food intelligence taxonomy, which is able to tag each and every item into these categories. Similarly, on the Instamart side, we have each and every item belonging to different levels of categories, which for ease of use, we just call it L1, L2, and L3. Say, for example, Robusta banana, then it will fall into the banana category. That's fruits, and that's on fruits and vegetables, right? Now we wanted to understand, is there any correlation between the users who prefer a particular dish category? Do they also prefer something on the like L2, L1 or L2 category on the Instamart? And like, yeah, we were extremely excited to see that there is a very good correlation. See, I'll take a couple of examples. See, if you see here, those users, I'm here, the users are, okay, I'll come to this likers later. Yeah. If you take a user who has ordered, like this is a percentages. So the percentages of food orders, which has a paneer item. It could be paneer butter chicken, or it could be paneer butter masala, whatever. So it has a paneer item. We also see that there is a very good correlation that as the number of orders containing paneer increases, then there is also a very good correlation between the dairy products that they order. Like it could be cheese or paneer or milk. In fact, I think that would be like my graph. I would have ordered like a 50 or plus paneer lababdar from Ball company. And yeah, I would order paneer like very regularly. Even if you see, say for ice cream, right? For the users who are having lower orders, percentage of orders, like those who don't have orders, they would order like 14% of those users would order, and this is again in their first order on Instamart. Like this is all with respect to the first order. Like we have their history on food. What do they order in the first order? So now we see that the ice cream lovers, those who are ice cream lovers on the food app, as the percentage of orders which contain ice cream increases, the number of orders on the first food app also increase that contains ice cream also increases. Yeah, I think like looks like a lot of plots are relevant to me itself. Okay, so now, and very similarly we see here, even in terms of the food categories, right? Like if we see that the users who are like sandwich lovers, again the category sandwich, it's called, we've just made it for the ease of the analysis. We've told a sandwich lover is if 50% of their orders have sandwich in, at least one sandwich item in it. So we see that those who are sandwich lovers actually have a disproportionate amount of, say, cheese, bread, and these in their first orders. So we were like extremely excited to see, okay, there is a good overlap, there is a good correlation. Okay, let's read some papers, implement it, and we are going to improve the new user recommendation. Okay, and one of the very prevalent methods that's there in cross-domain recommendation is embedding and mapping, wherein what we have for those who are not very, if you don't know what is embedding, it's a simple way of putting how do we map a customer or a personality to some mathematical vector. We can go by that. Like a chicken lover will have one vector, because at the end of the day, programs understand numbers. Now, how do I convert people and personalities to numbers, right? We'll go with that. I mean, maybe we can discuss about how do we generate embeddings. But for now, let's say each of the user, like it's like a signature vector for me. Each of the user has a vector which defines that particular customer on the platform based on what they have ordered. So now what we will do is we have a customer representation based on what they've ordered in the food domain. And we have a customer representation based on what they have ordered in the Instamart domain. Now, mind you, this is for the users who have been on a food domain and have made some order, or the first order on the Instamart. Through that, we will learn, so that next time when a new user comes to Instamart who is there on food app, we know we can map it and get their preferences. Now, this is like a very, whatever literature you would see, it would be some form of modification of this basic principle. You learn a mapper between the two domains and use that mapper. Okay, yeah, we went ahead, implemented it. And these are I'll not go into the details of it, but at the end of the day, we learned basically the mapping between the two domains and implemented it for our use case. And then what happened? It did not even beat the popularity model. Okay. Okay. And let me just cover this. Yeah. So the candidate set for this is basically because it's a new user, we took the popularity base itself as a candidate set, which means to say that all those orders which have been ordered for, say, some amount of time or some quantity in a particular pod, that is like, say, about 200 or 500 odd orders, that is taken as your candidate set among, say, like hundreds of thousands of items that may be there in Instamart. Only some might be popular at a particular pod. So that is like your candidate set here. And again, there is a recency weighting on it, because during, say, Diwali, Navaratri, some items become more popular, and say summer's ice cream become more popular. So to capture that, we have that a look back window of some days, and also we have baked in some items may be popular in a different slot. So we have baked in that a look back period of some days, and we have also baked in the locality, as in what might be popular in a Bangalore pod is not same as what is popular in Delhi, and the time slot, afternoon, morning. So based on this, we have a set of items to be ranked, and we ranked it using the embedding mapper, because we have the food-based embeddings and we have grocery embeddings. We try to link it, and yeah, not very good. Then we were like, okay, we are really missing something here. I mean, while it is working for the use case discussed in the paper, I think there is something different in our use case. Like, what is that is different? That is fundamentally because that hyper-localness is not coming to the picture. What I mean by that is, let me go here. See, what in the mappings, whatever we were doing is, we were trying to learn, okay, a person who liked, say, okay, maybe I'll just go to this. A person who likes, say, pizza in, say, South India would have probably ordered, say, bisibele bath in their first order, right? And a person who liked pizza in North India might have ordered, like, say, ready-to-eat paratha, or maybe in Gujarat they would have ordered dhokla. Okay, I'm just taking some examples, right? So now when we are trying to map these item, like a very, very granular level, item level embeddings, right? That's where the model is kind of getting confused. I mean, because that is extremely coarse and extremely sparse data. While if you just look at it, what is kind of common to it? Okay, it looks like the pizza eaters are liking ready mixes. That level of granularity we didn't go when we try to model at a data level embedding, right? So that was one of the sparsity was there. The second part is the if there is any like the geographical or location level nuances, that was not getting captured. That is when we realized, okay. And the third point, yeah, again, there is like the sequential learning, as in there is first we learn the embedding and then we try to rank. Maybe that I will not get into the details now. But the main point of takeaway here is that item level is too granular and the geographical level nuances are not getting captured. So now what we did is, yeah, so can we do better? We did a hierarchical model. It's more like, is there data? Let us capture the nuances at the level that the data is there. Like, let us capture, okay, these kind of lovers, like, let's say ready to mix, if that is coming out well in the correlation, let us use it. If it is coming out well in the next level also, like say, for example, even if it is coming out at the level of ready to mix and say some rice items. So if that is coming out well in the data, then we can capture that as well. But those cases where it is that becomes very noisy, we should at least be able to latch to a higher level. So that's when we thought about having this 2-stage, where the first stage is kind of hierarchical in the sense that we will try to learn the correlation between the food preferences and L1 category, food preferences L2 category, food preferences L3 category. Item level is too coarse for us and let's not go there. And when we did that, so in the first layer, we had this item level product category mapper, and then we had location our ranker. So when we did that, this is basically the architecture of just what I said. And yeah, maybe the network details are not required here. The point to take away is we did like a more hierarchical coarser ranker, coarser mapper, and then to capture the geographical nuances that is anyway coming with the candidate set and any other attributes that we can always add in the ranker. So when we did that, yeah, maybe I think I can skip these. Do I have time? Okay, yeah, I have time. Okay, then I can cover. Yeah. So let me just then go to the mapper itself. How did we? In fact, like it's pretty intuitive what's happening here. Let's take this example. What we are trying to learn is we have the food preferences as input to the network, like the percentage of orders that is that is ordered by the user at a category level, and we have the item category level as the output, and the network tries to learn the mapping. It's very similar to the mapper that we were trying to learn, but just that we made the job a little simpler by telling, okay, you don't learn item to item, but you just learn category to category, because that is slightly coarser and the variances would be lesser and it will be less noisy. But having said that, if the next levels are available and it is not as noisy, okay, if it is possible to learn with confidence, then fine. So then we had like three networks, each of which, I mean, it can extend to whatever is the level of hierarchy in different problem statement. But the idea is to be able to learn at each level of the hierarchy, and then these will go as input to the final ranker. In our network, what we did is we not only took what is like the preference, which is the output of these networks, and we also took what is the rank. Say, for example, a 0.2 preference would mean like a very high score if it is actually the first rank. But 0.2 preference, that it's just a number, right? Like how will a network understand whether 0.2 is good or bad, right? So if 0.2 is good and it is like the first category among the categories, the 0.2 means it's good number. But say, for example, if the highest rank is 0.8, then that means to say 0.2 is not good. Like 0.2 would have got like the 6th rank. So what we did, we input both the absolute value, that's the probability of the customer liking or customer ordering such a category in the first order. We also put the rank to it. It's like and this we could do because there is interpretability to the output, and we could feed it in the way that whichever is, again, I come back to saying that each hierarchy, the ranks were available. So now having this, in the second stage, we have a GPT based ranker where all these things goes as input. And we see that while the popularity based score, which is basically whether that item is popular in that store for that particular slot and location. So while the popularity based score is coming as the topmost feature, definitely the other ranks and the scores are actually helping, and that's why we could improve. In fact, that's how we could beat the popularity. And here are the results. So okay, maybe I'll take a simple example here. What is a mean ordering position? That means to say that in the first app I showed you, right, like the list of items are displayed. Now what this shows is what is the mean position that the item is getting ordered from in the first order. So we see that compared to popularity, I mean, this is a relative number I've added here. So compared to the production model, which is the popularity based model, we are seeing that the mean rank has decreased, which means to say that we are showing better ones early on and people are clicking on it and ordering it. Whereas the earlier, the EMR method that I showed actually was doing poorer, because of all the issues that I discussed. So this, I think these like the other metrics are also indicative of that. So we can see that. And also this is a very interesting observation. It was very intuitive that this is how the model should behave. It was very nice to see the output that way. If you see, what would you expect that a customer who is like a very old history, who's been ordering very actively, then that means you say, I know very well about this person. I should be like bang on. I should tell him what is in the Instamart, right? That's exactly what we are seeing. Those customers who have richer history, we are able to, if you see that NDCG, right? The NDCG gets better. That's basically, again, similar to your where is the order coming from. It translates to that. So if you see that higher the order on food, we can see the higher is the NDCG on Instamart, which means to say that we are able to guess better, or we are able to predict better what is the item they will order on the first order, right? So the longer you have history and the earlier, I mean, it's obvious, but it is good that it happened, right? And because that essentially means to say that this model was able to capture those correlations and bring in that nuances to the Instamart side. And definitely extremely happy that we got these results, and also we were able to submit for the paper. And just one point I want to add here, that while this we are talking about in the context of food and Instamart, I think this is like a very, very general like a solution, because what it says is if you are having too granular kind of mapping, or if you have hierarchies in your system, you are well off exploiting those hierarchies than otherwise, right? I mean, there is sometimes what will happen is you may not have a natural hierarchy, but it is good to explore if you can create some segments, if you can create some cohort of users, and then define those hierarchies or segments and do the mapping across segments, because very, very granular level might get noisy, and though like the cross-domain recommendations, the knowledge transfer should work, we might not be like applying it in the right way to make it work. So this algorithm, while it is applied in like from food to grocery, I think it's a very general concept and can apply to various other use cases. Okay, these are the recommendations. I guess that's it from my side. I'm open to questions. Correct. Right here, what we do is in this ranker here. See, generally what we have is either in the repeat user or it could be in the new user. We will try to see to it that we don't recommend like the same categories within like the alternate positions would be coming from different categories. So it won't be milk, cheese, paneer, right? So it could probably be milk, then it could be some tea powder, something like that, right? So we will see to it that in the ranking algorithm, we will introduce that alternate category, and there again there is a weightage, like how much you want to mix. Like, do you want to mix it the very next one, or you want to mix it like the number of positions that you want to take?
Thanks a lot for your presentation. So my question is that priority listing for brands as well as for restaurants is a revenue stream for Swiggy. Not sure if it's the same for Swiggy Instamart, but just wanted to understand a little bit more on how that is factored in the recommendation engines, and also how that impacts placement of items.
Yeah, actually, of course, we have product monetization and restaurant monetization, and in fact, like my team only works on ads recommendations. So in both in Swiggy and on product recommendation in Instamart, we have specific slots. Like, say for example, if you go to the Swiggy app, then there are, like, say in your first app it could be like say 147, or in your vertical listing it could be 135. So there are fixed slots, and based on once the optimum, there is a ranker. The ranker has an objective. Let's say for example, it is trying to optimize the click-through rate. So the organic listing would come based on its objective. Let's say it is based on improving the conversions, whereas the ads recommendation could be a mixture of both the CTR and the CVRs. So what changes is what is the objective for the ranker. Though the candidate list itself might be similar, let's say for restaurants, it would be the list of restaurants which are serviceable in a given area. The candidate list itself, the way there is a list, it's like two rankers. We have an organic ranker, you would have an ads ranker. The objectives of the two rankers would be different. And again, there would be other campaign parameters to be baked in. Say for example, if a campaign, as in basically it is like number of impressions of the ads, right? So if that has to be baked in, say for example, if a particular campaign is underburning, then maybe that factor has to be baked in. So it is like two rankers, then we mix the rankers. I hope answers that.
Hi. That was a very wonderful session. I think I learned quite a bit. Off the topic perhaps, but I wanted to know how embeddings for a particular product are calculated. So with respect to
how are they built? Is it what did you say?
Yeah, how are they built? So basically, when we talk about textual embeddings, it's very simple right now that we can train it on MLM tasks. But when it comes to perhaps e-commerce, it's very different in the sense we can't just train it on a plain MLM task. I think the embeddings would not turn out to be that good. So it needs to know that Britannia bread and some other type of bread are the same thing. So how is that done?
Yeah, actually we have a combination of both, just understanding the string and also understanding the categories. I mean, the way these embeddings are done, like we have one order-based embeddings and we have just like a pure catalog-based embeddings. So in a order-based embeddings, typically what we do, it's all again similar word-to-vec, prod-to-vec models only. But like given a cart, let's say for example, in a cart, say there is I'll take this example because we were surprised to see the output. There is suji rava, there is coriander leaves, there is chili, and let's say there is some bread and eggs. Okay, and there is similar cart. Let's say for example, then there is instead of suji rava, it is that shavge, that vermicelli. I don't know if you guys know it. So then there is some chili, and in fact we saw that the embeddings of this shavge and the suji rava came very similar because it is actually replaceable items. If you're preparing upma and all, I think people who prepare upma would know. Those embeddings came very similar because the way we train is we take the cart data and all the items in the cart are like one document that you would give to a TWEC, right? So, and that means to say that in the context of say upma rava, chili, maybe the coriander is actually the next one very close to it, and that is how the order-based embeddings would be trained on. Like, I mean, the nuance to it is we would actually break each of the name of the product itself as tokens. Then it could be some I don't know, some Shivani Bansi Rava, then there could be some Britannia Bansi Rava. So where we treat that Shivani separate, Bansi separate, that Bansi will connect, right? Because that Bansi as a string will be related to Rava. So those nuances the model can learn, and it will actually first understand what is this string. Now we also have a catalog based embeddings where along with the item, we also train the brand names. Like we'll put, say for example, if we put Tresemme, like Tresemme, some, I don't know, some hair fall controller, then that's a shampoo, right? Then there would be others like Tresemme and let's say Head and Shoulders, right? So then that could be like, again, hair fall shampoo, right? So then there is a connection between, because in the context of hair fall shampoo, this Tresemme and Head and Shoulders will get connected. So that's how even the brands, the context of brands will come into picture, and also the words of shampoo getting connected with the brands, that also comes into picture. So we use like both kind of embeddings, but the underlying model is again like our typical word to vec, prot to vec. Yeah. So that you got that, right?
Hi. I had a question. When you started doing this research, how did you, what sort of numbers did you have in mind, in the sense, how many users or what sort of data set, data points, what is the size you're looking at before you can get into a trustworthy prediction, right? Like recommendation.
As in, like, even why did we start on this project? Or what?
No, so when you started on, I get why you started on this. It makes sense, business sense, right? So, so I'm going to look at 100 users before I start.
Oh, okay.
So how did you get to those numbers?
Okay, I mean, here, like in Swiggy, the process is like very, what do you say? It's very clear in the sense that any new algorithm that you want to test, we have an experimentation platform. So we run an A/B experiment. Like A would be, these numbers of course are offline numbers. In offline numbers, at least if we see some delta, then that is when we start our A/B experiments. So in A/B, we'll go through the normal statistical significance, like what number of samples are required to see that this delta is significant. So that is like normal statistics. So I think the power comes to data scientists because we have this experimentation platform, and like we can run experiment left, right. So you make a algorithm change, like we start an A/B. So, and I think many of you would have seen that, like some of you are seeing something and some of you are not. That maybe we might be running experiment on someone. Yeah, I think it's very scientific. We run an A/B, we take the statistical significance. If it works, we scale it up to production.
So my question was, how do you guys keep a check that now you have deployed this model, right? 6 months from now, it's still giving really good results.
That again, we have like a holdout running. So at 2%, we have a holdout running, and we will keep comparing with the holdout if it is still holding up. Yeah, I think these are like.
And what are some other applications of cross-domain recommendations?
Oh, there is lots. Actually, I didn't cover. I mean, cross-domain recommendation now is like a sub area and recommendation itself. I mean, these are like everywhere. Like say, for example, Amazon would probably use it to, cross sell, or say, for example, people who would have bought some sci-fi books, maybe they will be recommended. What is that? Oscar, everyone, everything, everywhere at once, right? I mean, so this is like now everywhere, like literally you name a business, I'm sure everybody would be using, see, especially those businesses where they are into multi verticals. It is very easily, the data is easily available across. Say, for example, you have books and movies, but even otherwise, they wipe third-party data, try to match devices, and try to use those information and give the recommendation in their platform. I mean, in fact, there is this reference is actually very good, which covers like a huge set of applications. This one, the first one, cross-domain recommendation system, right? It covers a huge, you'll be surprised, some insurance company and some like I don't remember what was the relating domain. I was like shocked to see, okay, people are even looking at these kind of correlations. Yeah, I can share it offline, but yeah, it's a field in itself now.
Any more questions?
Hi.
Hey,
so,
yeah.
My question was, sometimes like you're doing this for one person, right? But sometimes the food order is likely representative of the group that I'm with. So let's say it could be from the family, or it could be from, let's say, a bunch of colleagues or a bunch of friends. So doesn't that throw off your algorithm in any way?
That is actually, that does, I would say. Yeah, because I think one of the pain points for us is to identify the personality itself. Like, is it a single order? Is it ordering for a family? Because we see that the data from the food side, like if you're ordering for a family, or rather maybe you're ordering for yourself at office, versus the amount of like the items that you would order on weekends, that is vastly different. Yeah, that more than like throwing off, I think these are the kind of features or like the cohorts or the customer profile that we try to learn and bake it within the recommendation itself. Like say, for example, in weekend, we know that you're willing to spend, or then you want to order from more premium restaurants. So that kind of weekday weekend behavior, that we do inculcate as features in the algorithm.
Thank you so much, Shubha, for the insight.
Thank you so much.
And making me order cheesecake every other day.
Sure. Maybe you should share your device ID. I'll put some discount.
So yeah, I know that how difficult is this recommendation part and how difficult is it to beat the popularity. So yeah, thank you so much for sharing the insights.
Thank you.